Now let's talk about the beer Lambert law and concentration, absorbance, all of that stuff. So in this curvette that I have over here, so curvette, you can think about it as just this sort of tube, container, whatever. It's usually made out of something like glass, quartz, something like that. And let's say if I put originally put some water in this container. However, what I decide to do next is I put some purple food dye in this curvette. So you notice how it's a little bit purple. Now, of course, the more purple food dye I put in, the darker the purple, right? The more purple it's going to get. So, um, in fact, if I wanted to find out the concentration of the purple food dye, right? Well, you can use something called spectrophotometry. All right. So, how do I find out the concentration of this purple food dye? What I do first is I get something known as a spectrophotometer, and what it does is it sort of shoots out light at a specific wavelength. So it spits out this light, right? Now the light is going to go through this container, and it's going to hit these food dye particles, right? It's going to hit these particles, and as a result, some of this dye is going to get absorbed into the solution, and because some of the light is absorbed by this solution, less light is going to come out than what's put in, right? So less of this light is going to put in because less of this light is going to come out because some of it's going to be absorbed. Now, the amount of light that comes out is going to be, you're going to find out how much light's going to come out from a detector. So there's going to be some sort of detector at the end that tells you how much light is coming out. And based on this information, we can find out how much light is absorbed, right? If originally, let's say, I don't know, let's just say I'm making up an example, but let's say if 100 watts of light are originally sort of pushed out by this spectrophotometer, and let's say the detector detects only 90 watts of light. Well, then from this information, you can conclude that, well, this solution has to have absorbed 10 watts of light, right? It has to have absorbed 10 watts of light. All right. And just so you guys know, your Corvette is going to be made out of something. Once again, it's going to be made out of something like glass or quartz or even maybe plastic. And the reason why it's made out of those materials is because, well, glass, plastic, whatever, that doesn't really absorb that much light. So this light is kind of just going to pass through this glass without it being absorbed that much. And then it's only the solution that's absorbing the light. So we want to minimize any sort of error that may happen, right? Any sort of extra absorbance that may happen with the Corvette. Now, based off of based off of how much is absorbed, we can actually find out, well, the concentration of a certain solution. All right. So we have this formula right over here. This is something known as the Beer-Lambert law, and this is just some additional information that I put in then. But basically, this is the Beer-Lambert law. The amount that's absorbed, the amount that's absorbed, right? That's going to be equal to a constant. This is just a constant, and then this is something known as molar absorptivity. Molar absorptivity just kind of tells you how kind of good a chemical sort of species, I guess, absorbs light at a specific wavelength. Okay, so how strong does that thing absorb the light, right? How good is it at absorbing light? Then you have B, which is the path length, which you can essentially kind of view as sort of the length the light needs to travel to get through the curvette. Okay, so if I have this light right over here, and I wanted to get through this curvette, well, how much does it have to travel, right? And a lot of the times, this value is going to be just 1 centimeter. All right. A lot of the times, most standard curvettes, when you're using spectrophotometry, doing the spectrophotometry experiment, right? Um, this distance right over here, the length of your curvette is just going to be 1 centimeter. That's most of the time, though. In chemistry problems, you might see like 2 centimeters or something like that, to make things more complicated. But just know that most of the time it's 1 centimeter. And then finally, you have the C, which represents your concentration. All right. So the amount of light that's absorbed is equal to a constant, which measures how good that thing is at absorbing light, multiplied by the length of the path, right? Path length. Because the path length also matters because imagine if you're shooting light out into this sort of tiny container, right? It's 1 centimeter. But imagine if you're shooting light out at a very big container, right? That's filled with your purple food dye, right? Remember, we're doing the purple food dye experiment, right? We have a solution of some sort of purple food dye. Well, notice how the light has to now travel through more particles, right? The light now has to travel through a more distance. Therefore, more of it is going to be absorbed by the particles. So notice how the path length plays a role in how much things are absorbing, right? The longer your path length, well, that means that the more particles, your thing has to pass through, and therefore more is going to be absorbed. And of course, we can't forget about concentration. Concentration plays a very big role in how much things get absorbed dye in this container. So let's say in my container right over here, I didn't put that much purple food dye. Well, because I don't really have that much purple food dye in my container, not much light is going to get absorbed, right? I mean, some of the purple food dye is going to absorb the light, but not much. However, as I put more purple food dye into my container, oh, now I have more purple food dye particles, and therefore that's going to absorb more light. So the concentration also plays a role in how much is absorbed. Now, the amount that's absorbed is also equal to this equation right over here. It's going to be log of basically the initial, let me just write this out real quick. So the amount of kind of light that's going to be absorbed, that's just going to be equal to log of, you can think about this I0 as the initial amount of light, or the initial sort of intensity of light. A lot of times it's called the initial sort of, incident light intensity. That's the word, incident light intensity. The amount of light that sort of enters your sample, right? So this is how much is being put in. And this I at the bottom is going to be divided by this I right over here, which is just how much light comes out. So the transmitted light intensity. And this equation kind of makes sense because, right, if you want to find out how much light is being absorbed, well, you have to find how much light is there initially and how much light is there at the end, right? If there's light in the beginning and then a lot of that gets absorbed, well, there's going to be less light at the end. So that could kind of, this equation right over here kind of contains that information. Let's just say we did our purple food dye experiment, and we just found out that when we have a blah blah blah. Okay. Now we did our food dye experiment thing, and we found out that when the concentration of our solution was 0.020 in terms of our food dye, it's going to absorb 0.200. Absorbance does not have a unit. When we did the second trial, we found out that as our concentration went to 0.040, well, this much was absorbed, right? So we basically used the amount we absorbed to figure out the concentration, right? And what I just want you to notice about this is that this is a linear relationship, all right? So this is just the important thing I want y'all to get out of this, which is that this concentration and the amount that's absorbed is going to be a linear relationship, all right? So, I mean, another thing to know is that this might seem a little obvious, but if you did not put any food dye inside of your, curvette, it's not going to absorb any, right? None of the food dye is going to absorb any light. So this is something. This is essentially your sort of zero mark, I guess you could say, right? This is just like a sort of obvious point that like every sort of one of these experiments are going to have a 0 point, right? And because this is a linear relationship, you actually only need to know one of these points in order to get the equation for your line. So for example, let's say that I got rid of all these other trials, right? Let's say if I got rid of all these other trials and I just had the first trial. So I know that when my concentration is 0.02, my absorbance is 0.200. Notice how I have 2 points. And because this is a line, right? You guys remember, if you have 2 points on a line, you can find out the equation for that line, right? Y equals mx plus b, right? Because this is a linear relationship, if you have 2 points on the line, you can find out the equation for the line. And now that you find out the equation for the line, then you can use this line to estimate sort of the absorbance values for each of the other sort of trials. You don't even have to do them, right? You can just use this line to find out, the absorbance for any sort of kind of concentration, right? Let's say if I found out the equation of a line and I wanted to find out my concentration when my absorbance is 1.2. Well, then I could just use the equation of the line. I can look at my absorbance, right? Let's just say if this said 1.2, I would take a look at 1.2 right over here. And I would see that this corresponds to a concentration of, and then you look at the concentration, and then, that would be your answer. So this is a really good fact that this is a linear relationship, right? It allows you to kind of estimate or even, predict, concentration absorption values. We're going to apply all the concepts we learned in this problem. You measure the absorbance of several standard solutions of a blue dye at this. All right, path length of curvette is this, and then here's the data. So we have all of this right over here, and here are the questions. Find the slope of the line. What does it represent? If unknown sample has an absorbance of this, what is its concentration? And what is the molar absorptivity, which is this epsilon symbol I put over here. Let's actually do the last problem because it's probably the easiest. So let's see. We know that the amount that's absorbed is going to be equal to a constant. This is the molar absorptivity multiplied by the path length times the concentration. All right. So in this case, the amount that's absorbed, well, let's just use trial 1. All right. But any trial is fine. I'm just going to use trial 1 here for my problem. So I know that the amount that's absorbed, 0.3, whatever, that's going to be equal to the constant, the molar absorptivity. I don't know that. It's going to be multiplied by the path length. That's going to be 1 centimeter, right? We said that's 1 centimeter. And this is going to be multiplied by the concentration, which when our absorption is 0.13, well, our concentration is 0.020, and then moles per liter, or molar, right? So when we solve for epsilon by dividing this by 1 centimeter and 0.020 molar, right? We just divide both sides by this, so this cancels out. All of this right over here cancels out. And it looks like we get this, which is 6.5 molar per centimeter. And yeah, that is going to be our answer. Now, let's find the slope of this line. So to find the slope of the line, we do our change in y. So in this case, remember, to find out the slope, it's going to be your change in y. So in this case, my change in y is going to be 0.260 minus 0.130, right? Our change in y divided by our change in x, or change in concentration in this case. So 0.40 0.020. And whoa, we actually get the same thing as we did for our molar absorptivity, right? When we calculated this one, we also got 6.5 1 over molar times centimeter. How does that make sense? Well, remember how equations are written in the form y is equal to mx plus b? Well, this equation is sort of written in y is equal to mx plus b. Let me show you. Y is equal to mx plus b. Let me show you the Lambert Law. The amount that's absorbed is going to be equal to the molar absorptivity multiplied by the path length multiplied by the concentration. This is sort of like y is equal to mx plus b. Notice how when my concentration is equal to 0, notice how I'm multiplying by 0 by whatever number this is. So the absorbance is also going to be 0. And that makes sense, right? We talked about how before, right? If we were to plot this on a graph, the concentration versus the absorbance, right? We always have to have a 0 at the start, right? Because if you did not have any concentration of whatever you're looking at, well, then it's not going to absorb anything, right? Now, remember how our path length is usually just equal to 1? So let me just get rid of this b because it doesn't really do anything to this equation. So I'm going to have A is going to be equal to our molar absorptivity multiplied by C, our concentration. Now remember that A represents our Y value, C represents our X value. If I divide both sides by C, I get that the molar absorptivity is going to be equal to A divided by C, right? So you can kind of see it, right? A represents our Y value. So, change in Y divided by C represents our concentration. So you can see change in X. Change in Y over change in X gives us our slope. So you kind of see the vision there, right? And yeah, this is kind of why our molar absorptivity is going to be equal to the slope of it. If an unknown sample has an absorbance of this, what is its concentration? So, we already have the slope of our line. And we know that the y-intercept of our line is equal to 0. Therefore, the equation of our line is just going to be y is equal to 6.5x, right? Y is equal to 6.5x. That's going to be the equation for my line. Or in the context of our problem, it's going to be the absorbance is just going to be equal to 6.5 times the concentration. All right. And now we can just solve, right? We know that the unknown sample has an absorbance of 0.455, so just substitute that in here. And then if we actually solve for the concentration, we get that the concentration is equal to 0.07 molar. All right. And if your school is generous enough to give you a graphing calculator, well, then you can confirm your answer. So we know that the equation of our line is y is equal to 6.5x. All right, it starts at 0, 0, which is good because remember that's our 0 point. Notice how when our, all right, let's see here. Let me use the data here to actually see if our line is correct. So when our concentration is 0.02, concentration is 0.02, my y value is 0.13. That looks correct. And yeah, that's going to be correct for all of them as well. We can also use Desmos to solve this problem, of course, right? If our unknown sample has an absorbance of 0.455, right? So if our absorbance is 0.455, 0.455, all right. So it's going to be, hold up, it's going to be this. All right. Notice how notice how absorbance of 0.455 corresponds to a 0.07 in our concentration.